Hi, everybody. It's great to be here. My name is Nicolas Leenaerts. I'm a psychiatrist from Belgium, currently doing a postdoc at Harvard University. I'm quickly just going to share my slides here. Okay, perfect. So artificial intelligence holds a lot of promise when it comes to addressing eating disorders such as anorexia nervosa or overweight and obesity. And in my view, there are three big domains in which artificial intelligence could help. The first one is screening. Diagnosing people with an eating disorder, overweight, or obesity isn't that much of a challenge. Mostly the diagnoses are behavioral. But screening people and identifying who needs more help than our regular care, that can be a challenge. And Emma de Schuytener will talk on this topic. The second domain is sensing when people need help. For example, when they're about to eat or when they're eating. Chunzhuo Wang will discuss that topic. And the third domain is support, identifying when people need support, what support they need, and I will be presenting on that at the end of the symposium. Let's move on to our first talk by Emma de Schuytener. She holds a master in psychology from the KU Leuven in Belgium and is currently a PhD student in a mind-body research group at the KU Leuven in Belgium. Emma, take it away.
Thank you very much, Nicolas, for introducing me. I'm going to share my screen. Let's see. Okay. I'm going to talk to you today about developing a clinical prediction model for persistent depressive symptoms after treatment for eating disorders. I'm going to start with a small introduction. So if you look at eating disorders, we know that they are complex psychiatric disorders and that they are often heterogeneous across individuals. And if you look at research on treatments, efficacy, we see that despite specialized treatments, often recovery rates are modest and relapse is very common. And we believe that one important contributor to the heterogeneity between participants or patients is comorbidity. And we see that often individuals with eating disorders have a lot of comorbid depressive symptoms. And research shows that even between 30 and 75% of individuals with an eating disorder meet the criteria for major depression. And we also see that this comorbidity matters. So individuals who have comorbid depressive symptoms also show more severe presentations, greater treatment complexity, and increased suicide risk. So if you want to improve our treatments for individuals with eating disorders, it's important to see how depression evolves during treatments. And we see in general that on average, when people receive treatment for their eating disorder, that their depressive symptoms tend to improve during treatment. And this is what we can see on this figure. So on the y-axis, you have the back depression inventory, so a depression scale, and you can see that the mean, the average at admission is higher than at discharge. But if we look at the literature and what we also see in clinical practice is that probably only around 20 to 47% of people that receive treatment for their eating disorder achieve meaningful reductions in depression. And this is also what we can see if we look at individual patients. So imagine that these two dots represent people who enter treatment with considerable depressive symptoms. So they score 40 on the back depression inventory at the beginning. And we can see very different trajectories over time. So we can have this one individual, for example, who shows the expected improvement in depression. So the depression drops during treatment. But for this other individual, we see that they remain persistently depressed. And of course, these are the patients that we worry about and that we like to identify early so that we can adjust our treatment. And this was actually our motivation for developing a clinical prediction model. So what we know is that our current treatments are effective for some, but not for everyone. And we believe that machine learning can offer a way to help with this problem. So machine learning can be used to detect complex patterns in clinical data that might not be obvious in clinical care. And we had the opportunity to use data that was collected by our collaborators in Germany with a large data set of more than 1,400 individuals with eating disorders. If we hear about the other prediction models earlier today, we saw 50,000 individuals, but in the field of eating disorders, this is already a lot. And We had electronic health record data, for example, demographic data on age, clinical data, for example, which diagnosis they had, and also as part of routine care, these individuals filled in a range of self-report questionnaires. And our goal was to predict at admission, so when they start treatment, who is at risk for persistent depression. And before I go over to the results, I would like to point out that there are certain challenges that we see a lot when we look at the literature around prediction models in psychiatry. And these are, for example, operationalization of the outcome, limited sample sizes, problems with model evaluation or interpretability. What we tried is to use open science principles as a way to mitigate some of these challenges. And this is a QR code to our open science framework page. And I would like to go over the workflow that we use, so the methods a bit more, and how we used open science in our project before I go over to the results. We started from this data set and got some information from the owners of the data about what type of information was there. And we started with the first challenge. So we needed to operationalize the outcome. And in psychiatry, you often see that operationalizing outcomes is not very straightforward. And so we thought about what counts as persistent depressive symptoms after treatment, and how large should this change be then? And we decided to include two different outcomes in our model, two different models with two different outcomes to see what the differences are. And first, we included an outcome that we called non-improvement, and the patients were classified as non-improvers if they didn't show a reduction higher than 17.5% on the depression scale. And the second outcome that we used was residual depression. So if they scored higher than the cutoff of 14 on the back depression inventory at discharge. And then the second challenge that we encountered, or that's common in the literature, is limited sample sizes. And if we, this is often, so if we look at machine learning studies specifically in eating disorders, but in psychiatry in general, we see that they often suffer from very small sample sizes with many predictors, which might lead to overfitting. And the advantage was that we could use this data set, which is relatively large for eating disorder populations. And we also conducted sample size calculation, which is, according to some reviews, also not very much done in clinical prediction models in psychiatry. And this allowed us to justify the use of 14 predictors. And what we did is actually we posted a pre-registration, which is a document that we posted on the Open Science Framework, where we, before we looked at the data, where we specified our research questions, our outcome, what predictors were available, our sample size calculation, and some other things as well. And then we go over to the third challenge, and that is robust model evaluation. So if you look at the literature and review studies, we see that often the models in psychiatry are trained and tested on the same data set. And this might lead to working very well in the data set that was used for training, but it might not really generalize to new patients. And of course, if you want to use these models in clinical practice, we want them to work on new patients. And that's why we use the workflow I'm going to discuss now. So we asked the owners of the data to split the data and first provide us with a training set of 80% of the total sample. And we use this 80% to then pre-process, to feature selection, to hyperparameter tuning, and all of these things to train our model. And we looked at how well our model worked on this data set. And then we posted the second pre-registration, where we really specified how our finalized models looked like. We also reported how well it worked in the training set, so we did internal validation. And we also shared all of our code. And then only after doing this, we were provided with the additional 20% that we then can use as unseen patients to really see how it works on new patients. So this really allowed us to separate the model development and the model evaluation phase to have a bit more trust in your models. And then the fourth challenge that is often seen is model interpretability. And this is a challenge more at the stage of the results. And if you look at the literature, we see that often machine learning models are described as black boxes. This is also called the black box problem. In the literature, we can see that clinicians are often hesitant to trust or to adopt these models if they don't know exactly how they work. And that's why, besides looking at the performance or the accuracy of the model, which is often looked at as a result, we also tried to look at what drives these predictions. So this is called feature or predictor importance. And additionally, we also try to look at whether these models can be used to support clinical decision making, which we did using decision curve analysis. Now I'd like to go over to the results. So how well did our models perform? You can see here that we had on the plot on the left, you can see our two different outcomes. And then for each of the outcomes, we trained an elastic net model and an XGBoost model. And we saw actually that for non-improvement, the first outcome, that our models generalized rather poorly with an area under the curve of 0.64 to 0.65. And if you looked at residual depression, then our models performed better. So it's also already very interesting to see that really how you define your outcome can be very important. And then the second question we tried to answer was what drives these predictions. And I've decided for the slides to put on two models because it was otherwise a bit too difficult to see. But on the left, you can see the features that were important for non-improvement. And on the right, you can see which features or predictors are important for residual depression. And how you interpret the plot is that if the predictor is at the top, it's the most important. If it is at the bottom, it's the least important. So what we can see that there are some predictors that seem to be important for both of our models, such as anxiety and phobic anxiety. So if someone is more anxious at baseline, it results in a higher chance of being residually depressed at the end of treatment. But what is also interesting is that some predictors, such as baseline depression, are very predictive for one outcome, residual depression, but not important for non-improvement. And what is also might worthwhile to point out is that there are some protective factors, such as higher life satisfaction or higher resilience, which actually buffer against the risk of non-improvement in depression. And third, we want to evaluate whether these models can be used for clinical decision making. And we used a method called decision curve analysis. And what this method does is that it looks at specific thresholds to see whether our model outperforms compared to very simple strategies such as treating everyone or treating no one. And what we saw is that at clinically relevant thresholds, our models actually provide a greater net benefit than either treating everyone or treating no one. And additionally, my colleague Nicolas, he developed a Shiny app, which can also be used to understand more how the model works. And maybe it's important to note that it's an illustration and it's not really ready to use in clinical practice, but you can see on the left certain baseline characteristics that you can fill in or you can change and then see what result is for the predicted probabilities of both of our outcomes. So for example, you can play with it a little bit and see if someone is more depressed at baseline, what the influence is, if the age is different, if the BMI is different. So that's how the app works. And now I would like to go over or to conclude with some take-home messages. So we see that depressive symptoms are very common and clinically important in the treatment of eating disorders. That routinely collected data already holds some predictive value. So what we did is use data that was already collected, so it wasn't really developed with our research question in mind, so there are some opportunities to improve it as well. And what's also interesting is that open science practices can actually be used to improve the trustworthiness in machine learning. And this may also help make it implemented in clinical care. And further work is needed before we can implement this. And if you have any questions, you can always ask in the chat, but also contact me directly.
All right, thank you very much, Emma, for your presentation. We will now move on to Chunzhuo Wang, who holds a master in electronics and ICT engineering from the KU Leuven in Belgium, after which he did his PhD at the same university together in collaboration with IMEC, and he's now currently a postdoc at the KU Leuven in Belgium. So what tells you is the KU Leuven is a great place to learn and work. So take it away, Chunzhuo. I'm excited to hear your talk.
Hi, Nicolas, can you hear me?
I can hear you perfectly.
Okay, I will then share the slide. Can you see my screen?
Yes.
Okay, hi everyone. This is Chunzhuo Wang, currently postdoc researcher in KU Leuven. I'm glad to be here to present the work on automated food intake activity detection using wearable IMU sensors. Well, first of all, my colleague Emma and also Nicholas point about the problems with eating disorders, and actually not only in eating disorders, but also in the nutrition for diabetes and overweight, obesity. The traditional assessment tool for dietary is 24 hours recall, food diary, and food frequency questionnaire. But this methods has limitations because they need manual input and prone to error, not suitable for long-term usage, and they're also not capable for continuous monitoring. So as as a researcher in engineering domain, we're thinking, can we develop automated and objective approach for the assessing of dietary intake while using sensors and artificial intelligence? Well, before the introduction of our work, I will first briefly introduce the wearable motion sensor, initial measurement unit sensor. It contains 3-axis accelerometer and also 3-axis gyroscope. It's mainly used to monitor or sense the linear motion and also the angular velocity of the sense itself. But if we wear this in our body, like a wristband or in the form of smartwatch, we can use this to sense our wrist or arm movement and also our daily activities. It actually has been widely used in physical activity intensity measurement, and here we are introducing how we use this for fine-grained food intake related activities monitoring. Well, here I need to give a definition of intake gesture in the context of using wearable wrist, in the context of using IMU wristbands. This colored area represents one eating gesture that using cutlery take food from plate to mouth and put it back, and this is considered as one eating gesture in the view of the IMU wristbands. And we finalize this task. It's actually twofold task. First is detection, means that given this time sequence, we need to know there are 4 eating gestures and 1 drinking gestures. And second is the segmentation, means we would like to detect the boundaries, the temporal boundaries, means the start and end point of each eating and drinking gestures. But it's actually not an easy task because different people eat their food or drink water in different ways, and it's also not equally distributed through your daily activities. You have high frequency eating during meal session, but you have sparse eating and activities out of meal session, and it's also imbalanced. Counting the total activity, the time used for your other activities, and also the time used for eating related activities just take less than 10% of your time. So this is a continuous human activity recognition task with emphasis on fine granularity and high variability. And then I will have a case study for this used by using this approach, eating speed measurement in near free living environments. We collect a data set that contains, the first data contains 34 participants and second contains 27 participants. We recruit participants, let them wear IMUs on both hands, and we let them do their daily activities from morning to the evening. Well, more importantly, we have a research assistant to continuously follow the participants and use cameras to record their uh, activities to make sure that we can annotate their from when to when they have eating gestures, not only in meal sessions, but also out of meal sessions. Then we applied deep learning model. I will not go into details of the architecture of the machine learning model. We use temporal convolution neural network, and the input is IMU signals. Output is three-class classification. Means the model need to give the prediction that the input data is eating or drinking or others. And here is the example of the input and our prediction. This represents the right-hand signals. It's 2 hour, 120 minutes, and it's represents three accelerometers signals from X, Y, Z axis. And this is the left hand, and the gray vertical line here represents the annotated eating gesture. Here is a red vertical line means drinking. So this is input of the model, and this block represents the prediction of our model. It's indicated in a green line. Well, here we couldn't see the details, but we can notice that in this area, we have high density of eating gestures in ground truth, and our prediction also has showed high density of detected eating gestures. It's actually represent 1 meal session. And if we zoom in, like grab 2 minutes, 2 minutes data, the gray vertical line actually is a gray interval represents the start and end of eating gesture, and our predictions also interval. This shows the granularity of the model. And once we have the output of the model, we need to do the evaluation. We apply typical classical conversion metrics to identify true positives. Means if in actual it's eating and our prediction is eating, then it's true positive. Or if in actual it's non-eating and our prediction is non-eating, then it's true negative. Otherwise, it's false positive or false negative. Well, once we identify TP, FP, FNT, we can calculate precision, recall, accuracy, and F1 score. These are the evaluation metrics used in machine learning. And here we used F1 score range 0 to 1, and higher the better. And we conducted sevenfold cross-validation in subject level, and this is the performance. Here I would like to just take your attention on this figure. It's for eating gestures achieved 85% F1 score, and for drinking it's around 90% F1 score. Okay, so here we first have detected the eating sequence from the IMU signal, and then because based on the previous example, we kind of know that if in the areas at high density of eating gestures, we are confident that it's eating episode. So we use a clustering technique called density-based spatial clustering of applications with noise to cluster this sequence into the segment or interval, which we consider as eating episode. And once we identify the time and also the number of eating gestures, we can actually measure the eating speed for the meal session. And this shows the results. The axis is the meal ID, and y-axis the eating speed with unit number of bites per minute. And the dark blue bar represent the ground truth eating speed, and light blue bar represent the predictions. So if you look at from right to left, you will see that when the ground truth eating speed increased, our prediction also increased, which shows a high correlation coefficient. And then we had a holdout validation that we train our model on FD1, and use the entire FD2 dataset as a test set. And we are glad to see that we still obtained a good performance with a little bit performance reduction. Okay, so previously we validated the approach in our internal datasets, and the next question is how this model performs on the external datasets. That's actually these datasets are not designed for food intake activity study. So we collaborate with University of Oxford wearable groups that they collected the Capture 24 dataset, contains 151 participants day. And they have in their annotation, they luckily they have the eating activity related labels. So we trained the model on our own data sets and tested on their data set. And you can see the bottom plot represent the overall statistics on the eating activities throughout the day from 5 a.m. to the end of the day. And the y-axis represent the frequency of the meal times on the entire data set. And the upper plot represent our prediction on the entire data set. You can see that it actually shows quite high overlap between our prediction and ground truth. Should be noted that this is on the health populations, health groups, and we then further validated such technique on the group of the people that with eating disorders. The private data sets collaborate with the team Emma and Nicolas. It contains 57 eating disorders participants data, and the participants were also two accelerometers, but using different type of sensors from morning to the afternoon in the hospital, and they followed more or less same schedule that you can see that they have from a 12:15 to 1, they have lunch, and also they have 2 snack sessions. So within this schedule, although we don't have a very accurate ground truth value, but we can more or less assess the performance of our approach. And this is the performance. I also draw the overall prediction statistics. The x-axis represents the time from morning to afternoon, and the y-axis is the frequency of the detected meal sessions. We can see that for the meal session, we actually have quite high correlation with the schedule. And for the early snack, as we detect 20, and for the snacks in the afternoon, we actually didn't detect it a lot based on our data. We actually have two, maybe there are two we think there are two potential reasons. The first is for the snacks in the afternoon, most participants use hand to take the snacks. Our models, one of our models' limitation that it couldn't detect quite well for just use hand to detect to eat food. It's more easier to detect eating gestures used with cutleries like fork and knife, chopsticks, or spoons. So then we go to the conclusion, future work. We first validated that it's feasible to use wearables and artificial intelligence for intake just detection, but we still need to improve performance, especially on the external datasets validation. And our future work is to explore its potential on applying such technique on patients with eating disorders in their daily life rather than just in the hospital trying to develop real-time or just in-time intervention using such combined with such technique. And acknowledgement with my promoters, Professor Badman Rooms from Electrical Engineering Department in KU Leuven, and also Edo Camps, the Nutrition Department in Wageningen University Research in Netherlands, Ask from KU Leuven Department of Neuroscience, and Aiden from the Wearable Groups of University of Oxford. And that is my presentation. Thank you for listening.
All right, Chunzhuo, thank you very much for your presentation.
Thank you.
All right.
Then
I will. If you end your screen sharing, then I can take over.
Am I still sharing?
Yes, indeed.
Okay. Okay. I will just stop it.
All right, perfect. Okay, great. I will present on the topic of improving just-in-time adaptive interventions for overweight and obesity. Struggling with your weight is not easy. We know that overweight and obesity lead to 35 million disability-adjusted life years lost per year across the globe. And the problem is that our current treatments aren't really that effective. Only 20% of people who go through a behavioral obesity treatment program will be able to lose 10% or more of their starting weight. And I get that. You learn a lot in therapy, but implementing that in your daily life is a challenge. But what if we could help people in their daily life? For example, with a smartphone app that monitors them and it has an algorithm which learns when it is necessary to intervene and which interventions need to be given. Well, that is the idea behind the just-in-time adaptive intervention. But this raises the question, when and how do you need to intervene in a just-in-time adaptive intervention? Now, there are multiple ways you could answer that question. But one thing that I want to focus on is reinforcement learning, or RL for short. Reinforcement learning is a type of machine learning where algorithms learn in which state they need to take which action to get a certain reward. For example, we could have a state that is described by the following variables: how much craving somebody's experiencing for food, their motivation to keep their diet, their social context, and their mood. These variables could then inform an algorithm on whether it needs to intervene or not. This in the hope that it would change the state of that person so that certain rewards would be achieved. For example, that craving would decrease and that motivation to keep diet would increase, and that this would lead to weight loss. In this case, that means that craving and motivation are mediators that actually drive the reward generating process, whereas social context and mood are interesting contextual variables that can help us inform, about whether you need to intervene, yes or no, but don't actually generate the reward. Now, this mapping of states to actions is called a policy, and you can develop a policy on the go during a trial, but you can also do it after the trial is done, trying to improve the policy that you've got. And that's what I'm interested in. I want to use reinforcement learning to develop a new policy that improves GDIs for weight loss. I said after a study is done, that means I'm going to need some data. And that brings me to the ADAPT study. In the ADAPT study, 159 people with overweight or obesity were enrolled in a 6-month-long trial. The first 3 months, people had weekly online behavioral obesity treatment sessions, and these were paired with a just-in-time adaptive intervention that wanted to prevent dietary lapses. After the 3 months were over, the behavioral obesity treatment session stopped, but the GTI continued for another 3 months. If we zoom in on the GTI, we can see that the participants received 6 surveys per day, asking them about their mood, their craving for food, who they were with, whether they were around tempting food. And that data was all put into a supervised machine learning model. And that model tried to predict whether people were going to break their diet or no. If the model said the risk was low, there was always going to be no intervention. If the predicted risk was high, there could be no intervention or a risk alert saying, oh, we detect that you're at risk for a dietary lapse, or there could be an active intervention trying to help people with their emotional regulation or other interventions. This with the idea that would prevent dietary lapses. So we've got a study with a GTI, with data, but it doesn't use reinforcement learning and it's not optimized for weight loss. So we want to do that. We want to use reinforcement learning after the study is done to improve weight loss, and we chose here to improve weight loss at 3 months. You will now see some results that are a preparation for a pre-registration based on the data of 24 participants. Now, to develop a reinforcement learning algorithm, we need to go through several steps. We need to build a conceptual model, engineer our reward, learn the action values, optimize our policy, evaluate our policy, and then interpret it. Let's start with the conceptual model. Why is that important? Well, reinforcement learning algorithms can do some crazy things. For example, if you tell them to solve climate change, they might learn that they need to get rid of all human beings because human beings lead to climate change. And we don't want that. We don't want to harm people. We don't want to harm our patients. So we really need to think about, our actions, our reward, our state. In this case, our reward will be weight loss. Our actions will be the same as in the original trial: no intervention, a risk alert, or an active intervention. We define several mediators that we think really drove the reward generating process. In this case, seeing your diet as a priority, having confidence in keeping your diet, not experiencing craving, and not experiencing hunger. And besides that, There were several contextual variables that were also assessed at every time step, such as a person's mood, their social context, and whether they were around tempting food, yes or no. Now that we've got our conceptual model, we can go on and say, try to create a reward. And then you might ask, well, didn't you just define a reward? Well, indeed, yeah, we defined mediators and we defined our reward weight loss. But the problem is that we only measure weight loss once at 3 months. But reinforcement learning algorithms need a reward that's measured at every time step. We can solve that problem by actually saying, well, our reward at every time step is actually the mediators times a certain weight. And we can define a weight so that, if we add all the rewards together, we get the weight loss at 3 months. So we need to find the weights that give the best fit of our weight loss at 3 months. And the result is something you can see here. On the x-axis, you've got the different mediators, and on the y-axis, you've got weights. You can see that, seeing our diet as a priority and having confidence in our diet are positive predictors, positive mediators for achieving more weight loss at 3 months, whereas experiencing hunger and craving are negative predictors. This means that our algorithm will try to increase the priority and the confidence while decreasing craving and hunger, which is good. It's not trying to restrict our patients. It's not trying to give them an eating disorder. So we don't want to harm them. Once we've got our conceptual model and our rewards, we can then go ahead and do some Q learning, which is a synonym for learning the values of the action. Like in which state, should I take which action? Like what are the values of taking a certain action in a given state? So we take our conceptual model and we then apply an algorithm, which in this case, we chose fitted Q iteration. I do not have the time to explain it, but contact me if you want to learn more about that. So we take our conceptual model and our data, we put it in our algorithm, and it spits out action values. So we got a data frame with 3 columns. The 0 is no, not intervening. The 1 is giving a risk alert, and the 2 is giving an active intervention. And the cells are the action values for every time step, because the rows are the different time steps. So, okay, we figured out the action values, but this isn't actually a policy. A policy is probabilities. Like how often should I, take a certain action in a certain state? And that brings me to policy optimization. So we take our action values from the previous time step and then, use our policy optimization algorithm to actually get out action probabilities. And that's what you can see here. So we've got 3 columns: not intervening, a risk alert, and an active intervention. And at every time step, we've got probabilities that sum to 1. You can see that we used constrained policy optimization. What is that? Well, we don't want to deviate too much from the original policy that actually generated the behavior. For example, if you remember, in some cases, the algorithm in the old study would always give no intervention if the predicted risk for a dietary lapse was low. In this case, we never saw what the value was of giving a risk alert or an active intervention. So in our new policy, we're not going to say that we're going to take actions in those cases, because we never saw what happened in these cases, and we don't want to harm people. So we're going to constrain it and say that in these cases, we're just going to always give no intervention. Okay, now that we've got our policy, we can then see how well it works. We do that with an estimator. We take our action probabilities from our policy, and we get estimates out of it. In this graph, you can see on the x-axis the old policy, which is the behavioral policy that generated the behavior, and the new policy, that's the target policy where we want to go to. The y-axis is the estimated return. That's the percentage weight loss at 3 months. The red line here is the actual observed weight loss in the data, which was 3.8%. You can see that the red line falls into our estimates for the behavior policy with a mean and a 95% confidence interval. This is like a security check. We estimate the return of the behavior policy based on the action values that we estimated, and we want the real observed outcome to be in there, because if not, that would mean that our action values, our model, is actually wrong. So if we then go on and look at our target policy, that's actually the new one that we define, we can see that the estimated percent weight loss is higher, around 9%, and that the confidence interval does not overlap with the behavior policy and does not have the actual observed outcome. So it's actually better than the one in the original trial. In other words, the estimator says that if the people in the study would have followed our new target policy, they on average would have lost 9% of their starting weight. Of course, this might be overly optimistic, especially because in this case, it's still a complete case analysis. But it gives an idea that our new policy is better than the old one. But what does it actually mean? What is the policy? What did our algorithm learn? Well, to do that, we got to do some policy interpretation. We can take the policy that we got and actually calculate Shep values. That's a concept that comes from game theory, where you can look at how important they were to get a certain outcome. And in this case, we're going to look at how important features were to knowing, when we should give an active intervention versus no intervention. You can see the Shep values here on the left-hand side. The y-axis that's the different predictors that we put into our model. On the x-axis, you've got the Shep values, with negative values meaning that it was better to give no intervention, and positive values meaning it was better to give an intervention, an active intervention. And we can see a couple of things. The first thing we can see that it was better to give an active intervention when people were less tired. And that's obvious. Don't bother people when they're tired. The second thing is that it was better when they were not alone. Perhaps being with other people was, a risk factor for people breaking their diet. We can see that it was also better to give an active intervention when people were less confident in that they could keep their diet. And it was better when they were around tempting food. So we've kind of got an idea of what our policy actually means. But of course, these are very preliminary results. It's a preparation for a pre-registration, and we need to see how this pans out in a full data set. If you want to keep up with my work or read up on my work, you can visit my website here, which you can also access through this QR code. I'm very open to receiving any emails with questions or, if people want to collaborate. And the results I presented here are actually part of a larger project where, together with Susan Murphy, Lara Coughlin, and Stephanie Goldstein, I'm working towards better treatments for overweight, obesity, and cannabis use by using RL to optimize just-in-time adaptive interventions. All right, thank you very much. All right, I'm going to ask Emma and Chunzhuo to join me again. And let's discuss some things. So for the audience members here, don't feel afraid to ask any questions. We'll gladly go into them. I've got a couple of questions for Emma and Chunzhuo. Emma, first you put a lot of emphasis on open science and principles in your presentation. And if I'm not mistaken, you're the first one here to actually talk on that. Could you tell me a little bit, why open science is so important when it comes to machine learning?
Yeah, thank you, Nicolas. I think that we see open science being more and more used in psychology in general, but it's not very used in machine learning, as we maybe saw in this conference as well. And I think there are maybe two things that are important. First, I think it can really improve our quality. So there are common mistakes that are made in machine learning models that maybe are less prone to be made if you use open science. For example, you could, of course, get the entire data set to begin with and split it yourself. But then there are certain problems such as data leakage that, for example, you think you're really splitting your data, but you're still calculating your hyperparameters or centering your variables on the entire data set. And this is actually pretty common. So that actually can be avoided if we use open science principles. And I think a second thing is maybe that we could make our research more reproducible and really share with others our code and how it works to then more as a research in to really improve the treatment of eating disorders, for example, by working together and really working, starting from other research and really building on this. So yeah, that would be my take.
Yeah, I totally agree that, machine learning is quite complex and that, you need to decide a lot of things and that, there's a lot of risk of, kind of, improve your model in a way, that you're, adapt your model in a way that your results look more nicely. And that for readers of papers, it's very difficult to actually understand the decision-making process. with with a lot of papers still not, sharing their codes, online so that people can actually check what people did. But I can imagine that some people will say, well, I need to make so many decisions, and some decisions
Mhm.
might be on the fly. Like how, like they might be a little bit afraid to engage
Mhm.
in open science because they're like, I need to decide so many things, and some things I might not understand completely yet.
Mhm. I think one of the things is to see a pre-registration as a way to already think about your data analysis beforehand, but don't really see it as like putting yourself in some kind of jail or something. It's also
Mm-hmm.
possible to maybe work more with we're going to do this. If this doesn't work out, we're going to try this. You can also be quite open in your pre-registration and be even honest about things that you're just going to explore and don't know beforehand. So maybe we shouldn't be too afraid. And if some decisions are not possible to make beforehand, you can make them afterwards. And maybe it's also important to say that even if you deviate from your pre-registration, which makes sense often to do, you're learning yourself or something else happens, that it's also not a problem to just be open about it and mention in your paper, well, we initially didn't decide to include this predictor, but then this happened and we decided to do it anyway. So I think we
Mm-hmm.
should maybe see it in that light, and that would help.
Yeah, no. Open science isn't a jail. Just like
Yeah.
a way of documenting things so that it's clear to the reader and so that everybody can just follow along,
Mhm.
and understand what is happening. All right,
Yeah.
thank you. Um, Chunzhuo, one thing you said, very, piqued my interest. You said that the model works better if people use cutlery than if they just use their hands. And I was wondering why that would be the case, actually.
Uh, well, it's very interesting because we are using the IMU wristband, the motion sensor on the wristband. It's you actually detect the pattern of your hand movement. So when compare the difference between use your hand to pick snack and some other daily activities use your hands, there's a lot of similarities,
Hmm.
which can confusing the model when you move your hand to your activities. Is this eating or just fix your touch your hair or fix your eyeglasses or use napkins? And on the other hand, when people eat food with hand, not cutlery, they have a lot of styles. Well, if you just hang your food, put your mouth, put it back, it's okay. But most of the time, if we eat a sandwich, we just eat like this. And if we instead of moving with hand, we use our head to eat food.
Uh,
So this is actually the limitation of only using IMU, the hand-based approach for eating just detection, because it's the assumption is just when you eat food, use your hand. There's obvious hand movement, but sometimes, for especially for eating with hand, there's no very specific pattern for eating compared to eating with cutleries that we normally do this or chopsticks. That's more obvious in the view of the uh, machine learning training.
mhm.
Yeah.
And because you talked about the limitations of the the wristband sensor,
Mhm,
like
mhm.
um, perhaps like in an ideal world, like if there's no constraints or whatever, like would you like to work with other sensors as well, or like which other wearables could be used to improve the detection of eating behavior?
Well, there's already some existing studies that use smart eyeglasses that use just the camera on the smart eyeglasses to monitor, to detect your eating events in the computer vision way, but they have two limitations. First is a battery concern. You couldn't make sure that your smart eyeglasses can running all the time from morning to the evening, with the camera recording. And another is a privacy issue that not only yourself, but you're also recording someone the one around yourself, around you, which can be a risk. If I didn't consider this constraint, I may trying to combine the IME wristband with some sensor that monitor your muscle movement near your mouth or throat, trying to do the multimodal learning that once either we detect your hand movement or we detect your mouth or throat movement, that we can cross-validate the eating gesture.
Yeah, and yeah, and started this question like with hand versus cutlery, and I was wondering, like in the models, could you look at like which features were important, or how did the model learn to discern eating versus drinking versus everything else?
Well, that's a good question. Well, this task has been investigated for more than 10 years. So at beginning, we're in the stage of the engineering, feature engineering, that we extract features manually and then put it into machine learning model. In that case, we can have feature analysis, importance analysis to see what does model matter. And but now we using deep learning model like convolutional neural network and some other subtype of the CNN model, also transformers. We directly input the IMU signals without manual feature engineering. So in this view, we couldn't have a very deep analysis on in which factor that affects the performance of the model. But you propose a good question that we actually also should trying to introduce the interpretability for the current eating gesture detection model.
Yeah, yeah, I think that's a very important thing, because research shows that for clinicians and people to use machine learning tools, like people need to trust them. And Emma and I, we've worked with SHAP values, but in your case, with you've got so much data that typically that becomes computationally really, really, really expensive and not really an option unless you've got you want to spend a lot of money on supercomputing. So but still it remains like an important question, and just interesting, like what differentiates an eating behavior versus a drinking behavior. All right, that brings us to the end of our symposium. I want to thank Emma and Chunzhuo, my co-presenters, and to everybody watching now or later. Don't hesitate to contact any one of us. We would love to talk to you about this further. Thank you very much.
Thank
Thank
you, Nicolas.
you.